Our Data Plus project, Learning to Communicate, deals with looking at the inner workings of wireless communication channels and using CogRL exploration to increase accuracy. Interference occurs when a transmitted signal's frequency overlaps with that of other signals in the same channel, resulting in poor data rates. Frequency hopping tries to overcome interference by spreading these signals at rapidly changing frequencies.
First, we worked with Q-learning and frequency hopping. Q-learning is a type of reinforcement learning algorithm that learns from experience. It tests different states and receives a score for the result that each state produces. In this project, we wanted to change the center frequency of the carrier wave to avoid interference and maximize the data rate. During interference, the data rate is 0. When there's no interference, the data rate increases. The idea was to use the Q-learning function to learn the behavior of the interfering signal to inform how we can change the carrier wave in the future. So when our signal overlaps with interference, the Q-learning would lower its score for that state. We use different time, frequency, and bandwidth to define our carrier signal state. This is an example of the algorithm that we built. Here you can see that once it learns the optimal behavior for avoiding the interfering signal, and here it looks at the periodic movement of the interfering signal, it starts changing the center frequency of our carrier wave and maximizing its bandwidth to get the data rate to the highest possible point.
We experimented with different values of decay constants for a single bandwidth Q-learning and SARSA learning, which are two similar reinforcement learning algorithms. The results gives the optimal balance between exploration and exploitation and shows the superiority of Q-learning in the specific program. Then the same set of parameters are used on variable bandwidth frequency hopping. Because of the addition of this extra dimension, the program requires more time to learn, so the same result is not clearly observed. Potential future work includes experimenting with more parameters, developing more data visualization, and implementing OTFS, a more sophisticated modulation scheme.
This is what our flow graph looks like in GNU Radio. The cognitive engine is controlled by a Python script. When we execute this flow graph, the transmission we see, the horizontal lines represent our transmitted data signals, and the width of each signal represents its bandwidth. The yellow vertical lines represent our interference signals, and we can see that there is a constant interference signal and a periodic one. At the end, our program automatically generates plots. We have the performance rate plot and data rate plots. These plots are also automatically saved along with a text file. We can then analyze our collected data.